Good morning, everyone, and thank you for joining us today. So, my name is Christine, and I am from the Lakehead International Enrollment Team. So, I'm a recruitment officer here, and I am joined by my two colleagues today. So, I'll hand it over first to Laura.
Hi, everyone. Thanks so much for joining the session today. My name is Laura Puttis, and I'm an international recruitment officer here at Lakehead's Thunder Bay campus, supporting students from Africa, the Middle East, and Caribbean. And I'll pass it over to Dr. Alkhateeb to introduce himself.
Good morning, everyone. My name is Abedalrhman Alkhateeb. You may call me Abed. I'm an assistant professor at the Department of Computer Science. And today I'm excited to be giving this class about exploring binary tree today. Thank you so much. I would like, first of all, to thank Lakehead International for their invitation. And very soon we'll start our class. Again, good morning, everyone. Today we'll be talking about exploring binary search trees. It's one of the vital or very important topic in computer science. Just to give you an overview about this class, data structure usually it's the third course in what I call it the golden chain of computer science. You start with Com1, that's Introduction to Programming in C, then Advanced Programming in Computer 2, Com2. It talks about more of advanced techniques and object-oriented programming in C++. Then we have a data structure. Data structure, you can think of it as a tools to implement your algorithms, your programming in general coding. Advancing data structure will advance your career as well, because nowadays, most of the companies, they will ask about, hey, how to do things in an efficient way. As Christine's mentioned, please stop me. You can ask questions. If there's questions at the very end, I know QA in general, but I'll be, for interactivity, I'll be asking questions. Feel free, please, to chat. With that being said, let's start. Excited to start. When we say a tree, could you please, just to make sure that we're interactive here, could you just type whatever comes to your mind when you hear the word tree? Which part, what do you think of a tree? In general, not just in computer science. Any answers? Please feel free to answer. Just make sure. Guys in the audience, what do you think of a tree? What's the main component? Branches, leaf, thank you, branches. Diagram, thank you, Martin. Thank you, Alex. Barkash, branches, Arjun, branches. More, what do you think? Growing, thank you, over time. Amazing. One thing leads to the next, thank you. Yes, Katie and Sandra leaves. Thank you so much. Yes, please keep, being interactive just to make sure that my class is not that boring. All right. Now, let's define a tree in computer science. Yes, it is that object or creature in nature which has root, branches, and leaves, right? And it keeps growing. Thank you so much. You guys helped me with this definition. In computer science, to mimic that, we can think of it as a hierarchical structure. That means each level leads to the next. Again, I'm using your terminology. Thank you for helping me from the chat. And it's undirected. Undirected means it's like two ways streets that you can go up and down, down and up from either or. It is what we call it a cyclic. A cyclic means, let me just maybe get the pen and start pointing out this terminology. A cyclic means, there is there is only one path between any two nodes. For example, to go from Outlook, if you can see, can you just tell me if you can see my drawing? Awesome, thank you so much. Let's say we're going from Outlook to normal, right? There is only one path. This is the way to go. There is no other way to go. Agree or disagree? Do you see any other way, guys? Right? That's the only path between these two. Of course, you can go back and forth, up, down, bottom up, etc. Thank you for agreeing. Now, with that being said, guys, do you think if I have this link here, is this a tree? If I link sunny to rain. Do you think this graph is a tree now? What do you think? It's rhythm. Okay. Do you think it's a tree? What do you think? With the definition of a cyclic. No, it's not. Thank you, Sefas. No, it's not. Why? Because now look, between rain and outlook, let's keep X and Y. Now we have two paths. We can either use this road or we can use this longer road, right? Or path to reach from outlook to rain. All right, guys. So tree has to be, it's a graph in general, consists of nodes and edges. It has to be a cyclic. Cyclic means only one path between any nodes, any pair of nodes. It means it doesn't consist cycle. Look, guys, when I have this link now, it's a cycle between weak, strong wind. So it cannot consist cycle in this structure. Application, you have so many applications in biology, in AI, random forests, trees, XGBoost. In gaming, growing up, teenager, I used to play a game called Doom 1, Doom 2. It has many versions where they're doing sectioning. You either can go right to left, right? Then with that structure, they use a binary search tree to implement it. Game development, machine learning, programming, and weather forecasting, file systems, etc. That's the application of a tree. So to go with more terminology, we have a root. A root is like the node that has no parent, right? It's a root or a node with no parents. With that being said, what do you think the root is? Please type it. What's the root of this tree? Just to make sure that we all on the same side, should be A, right? That's the root. Okay. If I have a tree with only one node, see guys, a tree with only one node, that's say X. Do you think X can be a root? Just to help with the definition, do you think X can be the root of this tree? By the way, is this a tree? Just a graph with one node. Do you think it's a tree? Answers? My question, is it a tree? Yes, thank you, man. Yes, thank you, Martins. Any disagreement? I think we should all agree. Why? Because one node, it's a cyclic, right? We only have one path between X and X, right? We did not violate any condition of a tree. Yes. So here, X is the tree, it is the root, and it is the leaf. Okay, we'll talk about the leaf very soon. But before that, I would just like try to define a tree before going into the, the other parts. Do you think an empty graph, something like this, if my screen has nothing in it, do you think it's a tree, by the way? So we say, we already agreed that this is a tree. Do you think this is a tree? Yes or no? What do you think? Some textbooks, they say it's a tree. Some, they say it's no. But I would love to go with yes, it is a tree. So it's controversial. Anyway, now the root of this structure is the node without a parent. In this case, it must be A. Internal nodes, they are the nodes with at least one child. With that being said, can you mention some parents, guys, on the chat? Does B has children? Yes, then we can say it is a parent, right? Now, does C has children? Yes, then it is a parent. Do you think D is a parent or internal node, what we call internal node? Since it's not a parent, we cannot call it internal node. We call it external, that's the leaf, right? It is a leaf. You may say, hey, the leaf should be at the very bottom of the tree, but not necessarily. The definition of a leaf or external leaf, or external node, sorry, it's a node without children. So thank you, Mustafa, for helping me. Please keep answering. D is an external, right? Can you give me more examples of internal, external of leaves on this tree? Just type. Do you think A is a child? I don't think so. Or a leaf, right? Do you think B is a leaf? E, thank you. What else? We mentioned D. You guys saying K, J, and I believe I. H, where is H? Yes, thank you for helping me. Yes, H, thank you guys. Thank you, Sudishna. Thank you guys. Now, we agreed that those are the internals here, and the one at the very bottom here, they are the external. So what do you think A? A is an internal or external, that definition. We said A is the root, right? So A is the root. Do you think A also considered as an internal or external? So of course, it's not an external, but do you think it is an internal? Yes, because for sure A is a root, but still it is also a parent, right? So we can we can define A as a root and also consider it as an internal, internal node. Talking about ancestor. Ancestors, they are the parent. Let me just clear the chat. If you don't mind, where is the clear arrays all linked? Okay. Ancestor of a node, their parent, grandparent, all the ancestor of nodes. So with that being said, guys, what do you think of the ancestor of A? E. When I say what are the ancestors of E? A, B and A, thank you. A and B, sure, those are the ancestors of A. For I, they must be F, the parent, the grandparent, the great grandparent. So we have for I, F, B, A. Okay, guys? Yes, thank you, guys, Alex and all. Now, the depth of a node, number of ancestors. So with that being said, going back to I, what's the depth of I? It says how many ancestors? You told me that I has F, B, A. So what's the depth of I? Must be 3. Thank you. Right, guys? I need more participants. Yes, it's A, B, F. Then the number of the ancestors are 3. Then we can consider the depth of I as 3. Can you tell me, guys, what's the depth of F? What's the depth of F? 2. Awesome. Thank you, Toro. Thank you, Shan. Thank you, Arjun. Yes, there are 2. So we have 2 ancestors in this case. Right. Now, the height of the tree, be careful. The depth, we start counting from the root. You know, as you can think of it upside down, right? What's the depth of the root? As like the depth of the building, right? Should be how many level you're away or story you're away from the root, from the base. Now, the height is the opposite, or it's the same. We can say it's the maximum depth of any node for the tree. So you mentioned to me that the node, sorry, where's the, yeah, here we go. The depth here equals 1. The depth here equals 2. The depth of the nodes at this level equals 3. The height of the tree is like the maximum depth. With that being said, what's the height of the tree A? 3. 3, thank you. Yes, it's a 3. Thank you, Samuel, Shan, and Alex. It's a 3. Okay, guys, it's a 3. Now, with that being said, you know we have the concept of having C as a subtree. What's the depth of C? In this case, would be 0. What's the height of tree C? Should be 1, because the maximum will be here 0, and for all the subtree C, right? And the depth here will be 1. The maximum depth is 1. All right, what else? Descendant of a node, it's the opposite of ancestors. Like how many child, grandchild do you have? With that being said, what's the depth, what's the, not the, sorry, not the depth, I mean, how many children and grandchildren with S, childs. Okay, guys? With that being said, what are the descendant of F? What are descendant of F? If in the exam question say, hey, mention the descendant of F, men said it's I, J, K. Thank you all. Thank you, Mustafa, Shan, etc. Victoria said 3. I think Victoria, here you're mentioning the number, but to be in particular, they should be I, J, K. Those are the children or the grandchildren of F. Perfect. With that being said, what's the descendants of A? No worries. What the descendant of A? C, D, G, H. You see, that's the misconception. Shan, it is part of it, but it's not just for the maximum depth. It must be all of them. So, as Min and the other mentioned, Alex, all the other nodes except A. So the descendant of a root, all the nodes, all the children, grandchildren, B, C, D, E, F, G, H, I, J, and K. Right, guys? So all the children and grandchildren. Thank you so much. Those are important. Now, to talk about tree traversal, it's a visiting every single node in a tree. We say, hey, traverse a tree. That means we try to visit all the nodes within this tree. And why are we doing this? Basically, when you take computer algorithm after this course, we start using tree, right? Maybe to have all, let's say you're a salesman, you want to visit all your clients today, then you can have them in a tree and then try to traverse them. Traverse them means to visit them. Say, hey, I would go to E first, then B, F. You can come up with different strategy, but what do? You need to put all your clients into a tree, and then using the methodology you created here, you can try to create a program to visit all the clients. Now, traversal means visiting. We have so many techniques for visiting. Of course, this is the algorithm here. Within the class, usually we don't cover coding, but in the labs, we cover coding. Just give you an idea how we do coding, right? That's in C, but usually we teach it in C++. Oh, sorry, here we go. Right, so for example, to get the depth, you choose the root, right? And then if the root equals the V you're trying to visit, that's the depth of V. Let's say depth of E. The first question is E equals the root? No. Then what we do, we go to the else, we say return 1 plus the depth of the parent of V. We said VF, right? What's the parent of V? Then B, right? Will be 1 plus the depth of A, which is 0. Then will be 0 plus 1 plus 1. The depth of F will be 2. You know this technique? What do you call this technique, guys? Do you have any idea of like a function calls itself over and over again? You see this function? It calls itself over and over and over until we reach the base case, until we reach the root in this case. So recursive. Thank you, thank you, Martin. Amazing. We call it recursive. So the function at this level, a level of, sorry, keep missing the mouse here. At level of G, SG is the root, no? Then we go to the else, should be 1 plus the depth of the parent. So we're calling the depth again, but the problem now is shrinking by 1 level. Keep shrinking until we reach the base case, which is the depth. We're returning 0. At this level, we're returning 0. 1 plus 1, that's 2. That's a recursive function. So Mustafa is saying, so mainly which programming language do you use for teaching programming courses? We use C, C++, but Java is part of the teaching at the year 3. we use Java for object-oriented. By the way, we're covering object-oriented in C and programming too as well. Yes, keep asking questions, that's fine. Now, the height of the tree, again, that's the function for it, which is for any node, we assign the value 0, and if it's external, we do the maximum of its own children. Now let's talk about traversal, visiting a node. Look at A, B, C, D. We can visit these nodes. Can any of you guys give me a criteria on the chat how to visit all the nodes here, starting from A? Or maybe we could start from H, but starting from H is maybe difficult. Let's start from A, from the root. Like, do you think, how should I visit A, B, D, E, H? Do you think maybe to take them level by level? Let's discuss them. Should we maybe go to visit B, then go like here from A, go visit B, then come back, then go visit C, right? Come back, that's level by level. So now I visited A, and I also visited B and C. Do you think this is a good technique, efficient technique? If you have two sides of the city, right? Two sides of the town where you live. Okay, do you think it's nice to cross the bridge between our border, or like cross the highway between these two cities? Not efficient, right? We go to B, come back, and then we go to C, come back, and then we go to the children of. Thank you. It's inefficient. Why are we discussing efficiency? Because as a computer scientist, you're using I hire you, right? I hire you, my company, to use these resources efficiently. If you don't, afterward, I'm sorry, you'll be getting this nice email from HR saying, with our unfortunate, wish you all the best. So we don't want to go that, right? We need to use resources efficiently. Right, guys? Now, what may be efficient, not to go level by level, maybe let's have them side, then visit the other side. Maybe we can visit this part, the east part of the town, right? Then cross back to the western, oh yes, the west, it's the opposite, sorry. This is the east, this is the west, right? Okay, so you're giving me Prakash, you're giving me an example. You can go by A, B, D, H, E. Okay, this is good. Right? Maybe then we can cross to C, F, G. Right? Maybe we could do that. Awesome. Now we'll be discussing 3 ways to traverse a tree. Something we call it in order. In order, once we start filling this tree with number, it makes sense. Then if you fill it with 1, 5, 10, 15, then once you visit it in order, it will give you this number 1, 5, 15, 10, 15, sorted ascendingly. Right, guys? But how we do it? It is left. Let me just erase. It is left, node, right. Okay, left, node, R. So we go left, then node, then R. But with a little bit of a tweak. Yes, how? Now, we start from the node, from the root, X here, X equals A, from the root. And we're gonna ask, A is L or N or R? What do you think? A in this case, is it the left or node or R? Should be, what do you think? N. Thank you. N. Thank you for all the answers. Now, since it's N, we're going to ask this question. Does A has a left side? What do you think? Do you think A has a left side? You might say, is there a tree has no left side? Yes, it could be A going to the right side with no left side, right? It could be A and C, for example, right? But without a left side. But in this case, does A has a left side? Yes. So we don't visit, we don't print A. We go to the left. We visit the left. Again, B is a subtree. It is a root for its own tree. The question, Does B has a left side? Does B has L? Yes. Then we should go to the left side, D. Now the question, does D have a left side? No. Then we can print D. We can print D. That's the note. We print, usually N means print N, print. Okay, guys, print. When we reach the node that has no left, we print the node. We can print now. Now, we go back to B. Does B has left side? Yes, but already visited, marked. Then we can print B. That's why printing B. We printed the left side of it, then we can do print node after the L. Remember, guys. Now, at level B, does B has right? We're done with printing N. We're done with here. The question, does B has a right side, guys? The answer should be yes, right? Now, again, we have to follow the same methodology for E. Does E has a left side? Right? Does E has a left side? Yes, then we go to the left. That's H. Now for H, does H has a left side? The answer is no. So what we do, guys, we're going to print H. So far what we printed D, B, and H. How? We print all the lefties of B, here. Then we can print B, just to explain for you. For H, we print all the left of H before. There is no left, then we printed H. Now, after printing H, we came here from E. Did we print all the lefties of E? Yes. So it's time to print, again, left. We got rid of it. Can we print E now? Yes, thank you, Victoria. We can print E. So far, we printed D, B, H, then E. Now, going back to B, for B, believe me, we printed the left, the node, the B, and the R. Here is the node. We printed all the lefties, which is D, right? And we also printed all the righties of B, that's E and H, all the children of the right side. So we can think of it L, node, right. For this subtree, we already printed the left, which is D, the node, and the right. Okay, now where we at? We are at B. We printed the left, we printed the node itself, we printed the right, then we move back to A. What did we do? We printed all these guys, which is the left. So now it's time to print what? What do you think? After printing the left of A, we should print? No, before the right, the node itself, Victoria. So we print A, right? And once we printed the left node, we can move to the right. Look at it. This is the A. Those all the lefties, all the L's. And if you notice here, we have all the rights, all the R's of A, right? R's of A's, any node in the right side. Now, after A, we'll go to the right. C. The question, does C has lefties? The answer should be yes, we have F. So we print F first, then the node C, and then it is G. Okay, guys, that's how we print it. All right, that's left, that's in order. We call it in order. In order, remember it, it's left, node, right. In any traversal, the left will be before the right. The problem with N, in the N order will be in the middle. Left, if you like, you're confused or you forget it in the exam, remember L should be before R all the time. Then in order, N will be in the middle. Pre-order will be the same, left before right. The only change that N will be pre, will not be in the middle, will be before the pairs of L, R. Okay, guys, now with that being said, for this tree, we start print the ends, of course. That one, always we're gonna print the end. Is A is N? Yes, then we print it. That's why printing A first in the pre-order. Then we will move to the left side. So you can think of it now as printing the node, then printing the lefties, right? Those are the L's. And then we move to the righties. How? After printing the node, we can move now to the left. B. B is a node itself, then we print it before moving to the left, right? Then D, doesn't matter it has a children or not, we're gonna print the node, that's D. Then does D has left? No. Does it have right? No. Then we're done with D. We go back to the subtree B. Subtree B, guys, what we printed so far, we printed B itself. We printed the left D, then we can move to the right side. Right side is E. For subtree E, what do you think? What should I print first? E, thank you. That's for printing E, the node itself. Then the left edge. And for E, we don't have any right. So we're done. After printing edge, we printed the lefties of A. Look at what we did so far. We printed A, all the lefties. Now we can move to the right side, or the right side of the tree, right? Now, moving to C. C is the node. That's why we print it first. Then we print the left of it, right? That's the node, left, then right. C, F, G. That's a pre-order. Okay, guys, so what's the difference? In order was L and R. Right, look, L always before R. In order will be in the middle, pre-order, the N will move to the left side. Now, can you guess for post order, what will be the order? We said always gonna have the L before the right. When N is here is pre, L, R, N. Thanks, Lowell. Thank you. Then in order, just to recall, where is the mouse? See here, yeah, sorry. Just to recall, N was here. That's in order. Post order, N must be after the R. So it will be L, R, N. Thank you so much, Noah. Having an amazing student like you make my life easier. Thank you. All right. So with that being said, let's just quickly visit this. L, does it have L's? Sorry, A, does it have L's? Yes, we go to B. B, does it have L's? Yes, D. D, does it have L's? No. Does it have rights? No. Then we print D. Right? Then we go back to B. B, what we did so far for B, we took care of the left. Now we should take care of the R side before printing B. So, does B has right? Yes. Then we go E. E has left edge. Doesn't have right, then we can print E. So look at E. We printed the left of E, R of E, right? We printed, sorry, for E, yes, we printed the left and there is no right, we printed E. Okay, now, after printing the left side of B, sorry guys, 1 second. Here, after printing the D, the left side of D, the right side of B, sorry, the left side of B, here, D, the right side, that's the right side, right? LR, can I print B? Yes, now we're good to do LR and we're good to print B. Okay, that's that. Now, what we did so far for A, we printed all the lefties. Before printing A itself, we have to print the rights. So we move to C. For C, we're gonna print L, that's F, G, sorry, R, that's G, then C, right, then the node itself. Once you do that, look at A, we printed all the lefties, all the righties, all lefties checked, all righties checked. Is it okay to print A? Yes, we can. It is safe to, to print A. Now, just to give you an example, why do we use post-traversal? Post-traversal, they're safe when we would like to destroy the structure. For example, if you destroy the structure from the node itself, what's going to happen? We're removing A from the memory, and then these guys, they will fall apart. They will get lost in the memory. We'll have no access to B, no access to C. Then there will be garbage in the memory. They'll be residing somewhere. We don't know where, excuse me. So we cannot destroy B3, the left and right. So what we do, for B, we destroy the lefties and then the righties. Then now it is safe to destroy B. Then I don't destroy A because still have a right side. If you destroy A, look at it, guys. We already destroyed the left side. What's going to happen in the memory? C, F, G, they have no access. There is no road to subtree C. With that being said, now we have what we call a garbage in the memory, right? It's like going to the beach and, after we leave, we have our garbage there. It's not efficient. Is not, it's not convenient for the users and for the programmers. Okay, guys. So now we'll talk about binary trees. Binary trees, it's a tree where the parent at most can have 2 children. Okay, so look at this tree A. Do you think this is a binary tree? The condition that it is a tree, there is no cycle, sorry, right? It's a tree. Is it a binary tree? We have to verify. Is there any node has more than 2 children? Right? Should not. Then I think this is a binary tree. Now, yes, thank you, Noel. Null and all, imagine if I have a children here in the middle called Z, for example. Do you think my tree now is a binary tree? No. Thank you, Victoria. Why? Because one of the nodes violating the binary policy. The policy here that any children must not have more than 2 children, right? With that being said, do you think a tree with only 1 node, let's say X, do you think this tree X is a binary tree, by the way? Yes? No? It is yes. Why? Now, X has the right to have 2 children at most. So that means in a free world, you decide not to have a child, or to have 1 children in this world, virtual world, or to have at most 2 children. So my right not to have at most children, I don't want to use it. That's fine. Okay, so this is a binary search tree because it did not violate the condition that you cannot have more than 2 children. And it is in the text box that even the word with nothing here, with a blank, it's a binary search tree. Okay, guys? So that's the violation. Now, once we have a binary tree, then potentially A could have left children. That's in the implementation. We'll do it in the lab. You'll see that any node will have a left and right. So any tree could have left children and or right children. Left children, right children, right? That's how we do it. So how? In the code, we're going to have a class called N or BST, sorry, can call it BST node. And it would have two pointers, one called left, one called R. So for A, we'll have a pointer B, or pointer that points at B, and that's the left pointer. And a pointer points at C, that's the right pointer from A, remember, from A. From B, you will have two pointers. The left will be pointing where, guys? For node B, the pointers of the left will be pointing at D. Thank you, Victoria. And the pointer R will be pointing at the right side. That's E. Okay, guys, and then we keep doing that over and over. All right, until we reach what? We reach that D, for example, has null, or you call it null, a left pointer, null, right pointer. Usually, you see it in the text box as like, you know, a solid kind of, sorry, trying to make it solid, pointer or node. Okay, that's how it is. All right. So a binary search tree, it's a tree that have the binary policy where a node cannot have more than two children. All right. Now, with that being said, do you think this is a binary search tree before I start? But this is a tree, binary tree, should be yes, because all the children at most has two. Binary search tree, it's a tree with this property that the node, look guys, please just, this is the last concept for today. So we need your attention for a bit. Where we have the node, we have the left and the right. It should be the node greater than all the lefties or the else, and the node is less than all the rights. Look, guys, is 6 greater than 1, 2, 4? The answer should be yes, right? You see, that's 6 greater than 1, 2, 4. Is 6 less than all the righties? Yes, 6 is less than 9, and 6 is less than 8. Now, guys, move, go subtree by subtree. Now you need to ask your question here, or you need to ask this question. Is 2 greater than the lefties? Yes, 2 greater than the lefties. Is 2 less than the rights? Yes. So we still in the binary search tree. So binary search tree is a binary tree, means the binary policy, and now we're adding another condition that all the lefties must be less than the node, and the node must be less than the R's. Say it from the opposite side. The R's should be greater than the node, and the node should be greater than the left side. Okay, guys? Now, just to remind you guys, if we traverse this tree using the L and R, the left first, the 6 has left, yes. This 2 has left, yes. This 1 has left, no, it's an L. So we print 1. Then we print what? 2, that's the node, right? We printed the left, we can print the node 2 before moving to the right, 4. For this subtree, we printed left and R. Now, for the upper subtree, we printed all the lefties. Now it's good to print the node 6 before moving to the R's. Now R's, does 9 has left? Yes, then we print 8, then 9. Look at the numbers, guys. What do you think of 1, 2, 4, 6, 8, 9? What's the property here of the sequence? The question, is it sorted or not, do you think? Ascending, thank you. It's sorted ascendingly, right? Yes. Why? Because we have the binary search tree where all the lefties less than the node and the node less than all the right side. Okay, guys, just before we wrap up, I want to ask you a question. Let me just erase it. Now, imagine if this guy was 5. Do you think this is still a binary search tree? So if here we have yes, thank you. Okay, I have another question. If this guy was 15, not 5, do you think it is a binary search tree? Yes or no? No. Thank you. Why no? Is 15 greater than all the lefties? Yes. Thank you, Martin. But 15 is not less than all the righties, right? So now we don't have, it is a binary, but it's not a binary search tree because all the nodes have at most 2, that's fine. But we violated the BST property where all the node is greater than the lefties and less than the righties. I think maybe it's time, right? Or can I go a little bit further? I think it's time. No, just to wrap up.
We have a few more minutes, so if you'd like to
Okay.
continue,
Thank you.
feel free.
Awesome. Maybe we can just telling you guys why we try to create a tree, why we try to create a binary search tree. You know, in the very beginning of your course, you'll be introduced to the first data structure, that's an array. Array looks like a corridor of, like here, my office and my colleagues in this floor. Hopefully you guys will have you here, you visit me in the office, other colleagues. Then you'll notice that we have a corridor. Believe it or not, it happened to be that my office in the very beginning of the corridor, then next. If you have a structure like a corridor or like an, what we call it, linear, then you always need to go through all the offices to visit the very last one. If this is the entrance, then always you're gonna have from A to B to C to D to E. So imagine if I have 8, I have 1, 2, 3, 4, 5, 6, 7, 8. If you're going from A to the very last, to the 8, then you're gonna pass exactly 8 nodes, right? That's a linear. The cost of my visit will be 1, 2, 3, 4, 5, 6, 7, 8 nodes. You'll be taking n-1 roots or edges. 1, 2, 3, 4, 5, 6, 7. All right. So the cost will be always n-1 because you'll take the first street, second, 2, 3, 4, 5, 6, 7. 7, it's 8 minus 1. N, if you have n of them, it's going to be n-1, the cost. That's in the linear structure. But guess what, guys? If you have a tree and it's balanced, going from either left or right, here, the decision, you know, it's like going to the street, in the middle of the street, you're looking for a house. The street, let's say you're facing the middle, that's 50, and you're looking for the house numbered as 70, you'll be taking right, okay? But if you're looking for the number 30, then you're taking left. With that being said, guys, when you take a decision, left or right, then you're reducing your cost by 50%, right? By 50. Now, you're either gonna take, let's say I'm looking for F. F is greater than A, then I should take right. That's the first one. Then F is, let's say it's less than, let's say it's a number here. less than, then I'm going to take this route. How many streets did I take here? 1, 2. If I have it linear, then it will be 1, 2, 3, 4, 5, 6, 7. But when you have it as a tree structure, if you're lucky, then you're visiting the first one. If you're kind of lucky, it will be the second one. Let's say you're unlucky, you're visiting the node down, then you will have the log. The log means how many times your problem can be divided. For example, 8, if you have 8 of them, it's at 8. Believe it or not, when you have 8, then the maximum you can take is a 3. 1, 2, 3. That's the log of 8. Why? 8, if you divide, because you're reducing the problem again by either left or right. Each time you'll be reducing the number of nodes by 2. The first reduction will be 8 to 4. Hey, no, it's not less than, it's not greater than, it's less than. So you're reducing half of the tree. Then you're reducing the problem by half of 2 of 4. Then it's going to be 2. Then you're reducing from 2 to 1. Right? Then just think about it, guys. To find finally that one decision, you have 1 reduction, 2, 3. 3 is the log of 8. It means how many times 8 could be divided to reach the value 1. So your reduction will be, think about it, if your town is this way, then if you're unfortunate that you have always to visit A, then your cost will be N. But if you design your town, maybe design it in a tree base, either left or right, then you'll say, hey, I'll take this decision. By taking the decision here, by left or right, you're doing 50% reduction. Okay, guys. I hope it was beneficial today. Let me know by emails. If you're around, guys, you want to book a tour, you can do it in computer science. Finally, I would like really to thank the Lakehead International and the other offices for inviting me today.
Great.
Don't
Thank
leave
you.
because you can ask questions, guys.
Yeah, perfect. I was going to say, let's open it up to any questions. So if you do have questions, feel free to put it in the Q&A, or if you prefer the chat, we can answer some questions right now.
Thank you so much, guys, for your kind words. If you have any questions, regarding this topic, regarding the program, feel free to ask, guys.
Perfect. We'll just give it a little moment. Oh, looks like there's one. Okay, so we have a question here. How can we use the binary search tree in a real life application?
Right. For any decision that we call decision tree, hey, it's windy, let's say it's sunny or not. If it's sunny, I'll play tennis. If it's not, let's take the next level. Hey, it's not sunny, it's a cloudy, not sunny, but it's not windy. Then I'll play tennis. But maybe if it's windy, it's not sunny and it is windy, it's not nice to play tennis. So we use it for decision trees, guys. We use it for a file system. Like, you can have a file system where you have the root and nodes in it. So many applications in gaming where whenever we have left or right to decision, yes or no's, we always use trees or a binary trees. Usually it's for 0 or 1 kind of decision. Just to give you insight, guys, you know that this computer science stems from 0 or 1 to P or not to P, right? Because at the end, everything is going to be turned into signals, either 1 or 0. Believe me, so many applications in the operating system to mimic this operation, right? The 1 or 0. Okay, the 2 decisions are always going to be there in our, in computer science applications.
Okay, and then we have another question here. Isn't it very hard to insert new values after a BST is built up?
Oh, it's not, because here I did not cover that, but let's say I'm going to insert 1. The question is 1 less than 6? Yes. Or let's say take 0. We don't have 0. Is 0 less than 6? Yes, then we'll move to the left. Is 0 less than 2? Yes. Then is 0 less than 1? Yes, then we're gonna add it here. Right, guys? That's the insertion. Is your question about insertion? Not sure the person asking. If not, let me know. Oh,
They
thanks,
said yes.
Alex. So see, in this case, you will take log n, right? Even more efficient than inserting into array, because inserting into array is efficient a bit, but the other linear, say dynamic or doubly linked list, then you have to go all the way to the last office or last node, then insert next to it. But here, the left-right decision, less or greater than, always gonna divide your decision from 8 to 4, from 2 to 1, right? Like 50% reduction, always gonna work towards the efficiency of decreasing big O of n. So to answer main question, it's not big O of n, it's big O of log n. Because if you have 8, then either left or right, then believe me, 8 to reach 1, you're gonna do reduction 3 times. That's big O of log 8 to the base 2 because it's a binary, right? So believe me, log 8 to the base 2 is 3.
Perfect. And it looks like we have another question here. How do we maintain the balance in a BST?
Yes, that's another question. That's another topic. Thank you for asking. You helped me. I should have done that. Because if you insert them in 1,000 and 99, it's not going to be balanced. It's going to be there is a techniques for balancing. One of them is a red black tree techniques, right? Where we do construction. Once the branch of the tree start going to the right away we fix it, right? How we fix it? We make one of maybe the heavier node or the heavier side. We'll take the next node to be just to twist it. We say that this side is heavier. So what we do the heavier side rotation. Then we're breaking the tree a little bit more into the right. So we always gonna steer right and left to balance the tree. So many techniques. One of them is red-black tree, and one of them, we call it AVL technique. Also, it's covered within this course. Yes.
Wonderful. And I'm not seeing any other questions coming up at this point in time. So, of course, you are welcome to take a virtual campus tour with us. And as Dr. Alkhateeb mentioned as well, if you're interested in getting a tour specifically of the computer science department and areas, you're also welcome to reach out to him as well. So thank you so much, Dr. Alkhateeb, for that insightful lecture showcase today. We had a lot of students asking questions, so it made it a very engaging presentation and very great for all of our students to learn a little bit more about what is done in the Department of Computer Science. Thank you everyone for tuning in. And if you do have any additional questions, you're welcome to reach out to us as well. And we can always put you in touch with Dr. Alkhateeb directly too. Perfect. So thank you so much, everyone. Oh, did you have any closing words?
Oh, I would like to thank you, Christine and Laura, and thank you all for participating in my lecture. And just like not to ignore each other question for engineering, you may please refer to the Faculty of Engineering. They have a representative there, I believe. Yes, and thank you all again for participating and showing up for my class. Thank you, my pleasure.
Wonderful. Okay, thank you so much, everyone, and we will see you next time for our next showcase or live session. Have a wonderful day.
Thank you.